next episode of Klingberg Wing Mark II Development. I'm Rob Klingberg, your host. Today we're going to have a quick and I hope educational and interesting episode on aerodynamics, a special area of aerodynamics having to do with the sealing of gaps around control surfaces. And if you've been following with, you know I've had an issue with my wing with air leaking in the gap between the elevon and the main wing panel, causing premature separation of the flow on the elevon. Some very astute viewers wrote in and said, hey, wait, I thought when you let air go through the gap on a slotted flap, it actually increases your lift. How come this flow through your gap is worse? It's causing flow separation and extra drag, and the elevon's not working. I don't understand. What's the difference between the two? And it's an excellent question. Why are they different? I offered people some time to write in on the comments and take their own shot at it. And a lot of people hunted around and had the various pieces, but I don't think anybody put it together in one concrete, easy to understand answer. So I thought I'd give it a go myself and maybe provide a little bit of fun and education for everybody. So here's the issue that I have with my wing, or had. I've solved it now, is that the air is going through the gap between the control surface and the main wing panel. And it's becoming turbulent here above the control surface, rendering the control surface mostly ineffective at certain angles of attack. Now this is shown with the control surface not deflected, but mine's only showing up at significant angles of attack, like something beyond 10 degrees on the control surface. But you have the basic concept here, that it is leaking through and causing this flow to separate from the control surface. So that's the basic problem. And then people are asking, well, how is that different than slotted flap that you have down here? The flow comes in and it goes through the gap and over the control surface, in this case a flap, and actually increases the lift rather than causing the flow to be disturbed and separated. And good question. And the basic difference lies between boundary layer and free stream flow. When we're trying to solve a problem like this or understand a problem like this, it's very good to start with what we call first principles. What is a basic thing that I know about physics or aerodynamics that will help me answer this problem? And the most basic thing here is that on a slotted flap, you're increasing the lift of the wing. Okay. If you increase the lift, you're doing work. Because generating lift is work. In order to do work, you have to have energy to do that. The whole aircraft flying through the air is generating lift. And the work is being done either by the propeller pulling the aircraft forward or gravity as the aircraft descends. That is energy that's being put into the system to generate that lift. Well, the same thing has to be true here. And the energy that is supplied into the system is via the free stream flow off the lower surface. And my problem lies with boundary layer. And I'm going to explain that here shortly, but I want you to note the difference here. This area here on a slotted flap, the main part of the airflow is curved like this. Standard control surfaces like mine wrap around the nose of the control surface. They're C-shaped like this, and they wrap around a bull nose on the control surface. So that's entirely different than this process here. Okay. And we have to keep in mind that the pressure here at the lower surface of the control surface, when it's deflected down, is higher than it is up here. So the air wants to naturally go up through there. It wants to go from high pressure to low pressure. That's another first principle that we need to remember. So you've got to add energy, and air likes to go from high pressure to low pressure. Here's the difference. This is free stream flow, where there's lots of energy available. And we allow the free stream flow to go through here, goes on top, adds energy into the flow on top here. And this flow up here, and I'll sketch it in now, that is headed, well, I'll use these up here. This flow that's headed aft here, like this, is actually going from an area of relatively negative pressure to something that's relatively higher. Now, we just said that one of our first principles is air likes to go from high pressure to low pressure. So anytime we have an airfoil flying, getting the air go straight back, follow the airfoil, is a bit of a trick. That's why we have to design our airfoils in specific ways to prevent separated flow, because we're forcing the air to go from low pressure to high pressure. Air doesn't like to do that. And specifically on swept wings, if the flow begins to separate, it runs out to the wingtip. This is one of the reasons why. It's avoiding going to this higher pressure area here. So we're going from low pressure to high pressure, and we want this flow to continue to go back, so we add some extra energy to it. We give it some extra momentum. Air has mass, and we add energy into the system, we give it more momentum, and that momentum will help it stay attached to the surface. If it were a laminar boundary layer, we might actually turbulate the boundary layer, and that'll help it stay attached here also. So we can generate more lift with a slotted flap than we can with a normal flap. Now, that comes at the cost of drag. There's always more drag because the air flowing through this gap gets draggy. But when you're coming into land, you're not so worried about L over D, you're worried about L. You just want lots of lift. And if you got some extra drag, it's okay. You need to slow up the land anyway. So the trade-off is beneficial here. Now, in the case of a control surface, we don't have that rounded corner there. And we run into troubles with the boundary layer. Now, third and final first principle. The flow around all of these airfoils in the conditions that I find is incompressible. So air can only flow from the point that's closest to the gap, which is in the boundary layer. The boundary layer on this is about as thick as the diameter of the yarn that I have on my wing for tufts. And because of the shape of my gap, we are preventing the free stream flow from going through the gap because of how I shaped the front of the control surface, which is normal. We don't want the free stream flow going through there all the time to be very draggy. So the only air that can leak through there has to come from the boundary layer. This is the boundary layer. This is the free stream flow up here. This is inviscid flow. This is all inviscid up here. And this is viscous flow here. And this is the velocity profile. And at the surface of the airfoil, the velocity is zero. The air's not moving at all by definition. If you look at my wing, I have a square-shaped section on the inside of my wing here. These extend back, and they come very close to the control surface. Now, the only thing that can get around this sharp corner down here is stuff from the boundary layer. And if the boundary layer is not moving, or moving only a little bit, there's no energy in it. The energy has already been depleted via drag against the surface of the airfoil. There's no energy being imparted to the upper surface here. All we have is leakage. And that's why I started out the top of the chart here, the top of the board, with leakage versus flow. A lot of people that were writing in were, and as aerodynamicists, we always talk about flow. Nobody ever says leakage. It's not a technical term that we use, but it's really what's happening, is that the air is leaking through the gap and going out the top and disturbing the flow here and rendering the control surface ineffective if too much of this gets through. If this were rounded off here instead, and it was curved like this, well, then we would let some of the free stream flow through there, and the flow would stay attached on the control surface, but we'd pay a penalty and drag through the whole flight regime, and I don't want that. So what we have to do is join and seal off those gaps to prevent the leakage of the boundary layer through there, and then limit how much we throw the control surface so that it doesn't stall. The other problem that I was having was we're down at low Reynolds numbers because we're essentially standing still. The wind's only blowing 9 miles an hour. Reynolds number's about 500,000. That's right in the bad zone, and it's very easy to separate the flow back here. In normal flight, it'll be up around 1 million, and the flow will be much more amenable to staying attached here. So that's the difference. Free stream versus peeling off the boundary layer. Now, one last thing, in case somebody's wondering, well, why is it just a boundary layer? Why isn't some free stream going up in there? That's because the flow is inviscid. This is incompressible flow, and if you have a sharp corner here, the only thing that you can bleed off is the boundary layer. First, you're sucking the boundary layer up off the surface, through the gap, and out the top. And why doesn't it suck the free stream through? Well, as soon as you suck that boundary layer through, a new one forms. And it's just a continuously forming boundary layer. So the only thing that's ever going up there is the air that has no energy in it because it already was spent rubbing up against the surface of the airflow, creating drag. So there's the difference between the two. It's really pretty simple. Leakage versus a slotted flap or free stream flow, and whether or not you're putting energy into the system or just disturbing the flow up here. I found a really good study online. Somebody had a very expensive module for SolidWorks, and they did analysis of the control gap problems from students. And there's a link down in the description. I'll put a picture up here somewhere of one of their samples. They did a really good job on it, and they do a great job explaining how control surface gaps cause this problem, and how they actually, in this case, up at the top here, it actually promotes separation way up here on the main part of the airflow, which we were seeing on my wing. It's really bad. So by sealing that gap, we're able to keep the flow attached much longer and get the controls back to something useful. So remember, leakage promotes flow separation. Free stream flow will add energy to the system and help keep the flow attached and provide more lift from the airflow. So there we go. Easy peasy, pretty simple problem, and explained without any equations. So I hope that was at least mildly amusing to you, and if you liked it and you're not a subscriber, please subscribe and give me a thumbs up. That's always appreciated. And also down in the description, if you want to help out, keep my channel going and keep me interested in doing this, go over to Patreon, become a patron, and I got lots of goodies for you. Free merchandise, you get all the technical details. It's way cool to be a patron, and I'd love to have you over there. So go down to that link, click on it, and go see what you can get over at Patreon. And for today, that's it. And as I always say, fly safe and bye for now.